And welcome to Naughty Notes. Well, here we go with our second set of proofs. There will be six. And remember, we said depending on how you write, you might fit two or three on a page. In each case, you're going to copy down the diagram. Here's the diagram I made for you. You're going to mark up your diagram as necessary, then you'll complete the proof. Let's get this out of the way. Let's get to it. Now, just to show you, this is how fast you should be with your straightedge. Like, wow. I mean, that's that fast. I don't want you spending any more time than that to make your drawing. Just get it done. And of course you're going to label it, but you are going to use a straight edge. Yes, you are. And we'll just get to this one. We're going to say, notice, I'm going to write this down. I'm going to say my one given statement, angle A is congruent to angle 1. Well, that was given. And notice I marked the diagram as we did that. I said, okay, so I can see it. I can see that angle A is congruent to angle 1, given statement. Now, I'm trying to prove that angle A is congruent to angle 2. That's over there. So I already know that this is going to be the last thing I say. But how do I get there? Well, let me see. There's a relationship between 1 and 2 that you should remember. And you'll say, golly, I guess 1 and 2, what are they? That starts with a V. And yes, we just did a whole proof on this, and they are the vertical angles. You know that 1 and 2 are congruent, and the reason they are vertical angles. You're going to state that. You'll find that on your pink sheet, your postulate and theorem sheet, or you can just paraphrase it. But in our textbook, it's Theorem 2.6. If two angles are vertical angles, then they are congruent. Yes, I want the conditional statement, if then. This is a theorem, and as we discussed earlier, it does not work in the reverse direction. Its converse doesn't work. This theorem works. Now, angle A is congruent to angle 1 is congruent to angle 2, and you all remember from arithmetic in previous grades that that is the transitive property. If A equals B and B equals C, then A equals C. But this is how you wrote it in elementary school. We're going to write it from this class. For this class, we're going to say, how many angles in the picture? 1, 2, 3. Both angles, A and angle 2, are congruent to angle 1. So we're going to say, Theorem 2.1, row out of room there. Sorry about the spacing. Let's fix that. We are going to say, if two angles are congruent to the same angle, then they are congruent to each other. That's the transitive property. In our text, that comes across as Theorem 2.1. All right, well, let's keep this rolling because we've got, okay, we're going to blast through this pretty fast, but you can pause this anytime and make sure you copy down these diagrams nicely, and we're going to write them out. Think about what you're writing. Next proof. Okay. Well, I've got this diagram here, and I've got a little color coding so I can talk about it. Got the red segments, the blue segments, but look at the given. AC is congruent to DF. Now, when you mark that, I don't know, I teach my guys, use like a little dimension line like that, because you're trying to say that this whole segment is congruent to this whole segment. And you're also trying to say, well, these two segments are congruent. And I usually ask my class, say, hey, which ones are longer, the red or the blue? Say, and well, that messed up. We generally say, we really don't know. This diagram is the same as this one, because that's all the information we have. Anybody think it's a parallelogram? No, I don't think so either, because we really don't have any information. As a matter of fact, these three segments they don't have anything to do with the proof. They're just there, taking up space. But all that we can see is that if I've got this is congruent to this, and the two blue ones are congruent, now let me see. All right, then the red ones, they got to be congruent for some reason. And we know this is what we're trying to prove. Well, think about the operations of arithmetic. There's 4. Remember, a calculator that can only do 4 things: add, subtract, multiply, and divide. And right away, you're taking the long segments and you're taking the blue ones away. Taking away is the operation of subtraction. And for using the theorem sheets that I gave you, we're going to write it in a very specific way. if congruent segments, that is the two blue ones, are subtracted from congruent segments, that is the long ones, then their differences, or the differences, that would be the red ones, are congruent. Make sure you're writing it the right way, meaning you are using the subtraction theorem with segments, not angles. We got only segments in this picture. Well, let's just look at the next example to see how else we might use this theorem. Okay, so go ahead and copy down this diagram. Again, it's you've got an angle. You got two givens here. Angle PON. There's NO. That's the angle formed here. PNO. And we've got this one, PON, that are congruent. And then we also have these two angles are congruent. And I'll call those angle 1 and 2. Now, you might be tempted to say some things, and this is really the decoy. We're trying to see, what do we know for sure? Well, the fact is, given that in this part in the book, we don't know much. But if you said that they were bisected, you'd be mistaken, because nobody said anything about bisecting. However, I do know that if these two overall angles are congruent, and I take away these blue angles, then these angles must be congruent. The only conclusion I could have is that angle 3 is congruent to angle 4. Now I'm recording this with using numbers for angles, and I'm always hesitant because a lot of you guys forget how to use 3 letters. Remember, we could say angle RNP congruent to SOP. I hope you can still do that, but you got to be able to use numbers, use letters. Those are the angles we're going to prove congruent. And just like before, I'm going to take these angles and I'm going to take away these angles, and what I'm left with are these angles. That's a clear case of the subtraction theorem. Again, 4 angles in this well, hang on a second. Getting confused here. There's a lot of angles in this diagram. We are taking the overall angles, and we are subtracting congruent angles, those 2 in blue, and the differences are those 2 little red angles right there. So if congruent angles are subtracted from congruent angles, then the differences are congruent. Okay, well, let's keep it rolling, and we're almost halfway there. Okay, copy down this diagram. AFE is congruent to DEF. FC, that's this ray, bisects this big angle, AFE. And I know that this ray, EB, bisects DEF. Yikes. And I already know my conclusion, so let's just figure out why. Again, there's 4 operations in arithmetic: add, subtract, multiply, and divide. Here, since we know that these 2 angles, we'll say the base angles, AFE, congruent to DEF, those 2 are congruent, that's a given, and these are angle bisectors. The answer is in the very definition of an angle bisector. An angle bisector divides an angle into 2 congruent angles. So our division theorem that we use, if 2 angles are congruent, then their like divisions are congruent. In this case, they're halves. Could be thirds if they were trisected, etc. Hey, if anybody was sneaking ahead and saying, hey, this looks like an isosceles trapezoid, kind of looks like one, but remember, we can't assume stuff. So actually, it isn't. All we know is that the angle AFE is congruent to DEF. The rest of the diagram, we have no idea. So we can conclude this. Sounds kind of trivial, but that's what this section's all about. We're just learning some form. Okay, 3 more. Let's get them. Oh, finally, something with a little excitement here. Now, I've got 1, 3, 2, and 4, and don't tell me anything about those lines in a transversal. We're not on chapter 3 yet. All we got is these 2 lines cut by this other line. I guess we'll say it's a transversal. Now, let's mix it up. I'm not going to list the given first, because you don't have to. We're working on form. I do know something about angles 1 and 3. I know something about angle 2 and 4. I know something about vertical angles. If two angles are vertical angles, we proved that already, then they are congruent. So I could have that as 2 lines, or I could write that in 1 line. Angle 1 is congruent to angle 3. Sorry, I did tell you to mark it. You should be marking those congruences. Sorry about that. Don't know if I have the little tool for that. No, I don't. All right, so mark your congruence mark. Angle 1 is congruent to angle 3. Just put a little mark there. And mark that angle 2 is congruent to angle 4. So we know we've got 2 pairs of congruent angles. Now, I'm going to link together with this one. That 2 is congruent to 3. That's my given. Now, the given doesn't have to be first, but it has to appear before it's used in the argument. And right here, I'm going to say, just follow me here. The 1 is congruent to 3, 4 is congruent to 2, yet 2 and 3 are congruent to each other. So that's going to link them all together. I've got 2 angles, 1 and 4, that are congruent to 2 and 3, which are congruent to each other. Yikes. So 1 and 4 are congruent. This is the transitive property again, but you have to write this variation for 4 elements. In this case, those elements are 4 angles. Because you've got 2 angles. That's 1 and 4. They're congruent to congruent angles, 2 and 3. Then they are congruent to each other. Now, of course, it means all 4 are congruent, but our objective was to prove that angle 1 is congruent to angle 4. Yeah, I'm glad you got that down, but you'll be seeing something like this. You'll be seeing a lot of this kind of stuff in chapter 3. Let's keep it moving. Just 2 little more. Oh, I love this one. Love this one a lot. I've got a diagram here, and of course you're drawing this diagram, and I'm going to put in this line. Yikes, that's a lot of givens. Angle F, or angle 1, depending on, you can number them if you want, is congruent to the angle FGJ, or angle 2. So again, you can use letters. You're going to have to use 3 letters to describe this angle. And of course, you can get away with 1 letter on that angle. Maybe you should write it this way just to get used to it. And so that's one given. Angles 3 and 4 are also complementary. That is, angle H and angle HGJ are complementary. That is a given. And that GJ, this thing right here, is an angle bisector. Now, boy, a lot to go through here. I'm going to first make use of this angle bisector, and I'm going to declare these 2 angles congruent. Well, I guess I already marked them. So we're marking our drawing. Angle 2 congruent to angle 3. And we know that. That's the very definition of an angle bisector. If a ray is an angle bisector, then it divides the angle into 2 congruent angles. Awesome. So we've got one set of congruences here. Now, we know where we're headed. We're trying to prove that angle F is congruent to angle H, also known as angle 1 and angle 4. But don't be jumping the gun. Don't be saying anything about transitive, because no one said they're all congruent. Now, earlier on, we made a proof, and here's the argument. 4 is complementary to 3. Remember, that means they're not the same. Let's suppose 3 is 30, right? Or let's say it's 40. Then this is going to be 50. Well, if this is 40, this is also 40. And if this is 40, this is 50. Just to give you some numbers for a concrete example. So the argument that we have proven earlier this week says if 2 angles, that's these 2, are complementary to congruent angles, then they are congruent to each other. And we did a nice proof on that. And this is how you use it. And by the way, just like the vertical angle theorem, you know that this theorem does not work in its converse. If two angles are, well, anyways, you go through that in your class. It does work forward. Not everything works backwards. So that's your theorem. In our textbook, theorem 2.5. Right, I think we're just about out of time. No, we got one more. Okay, I gave you lucky 7. Now, and if we did this live, and we do, this takes a whole class period, so I know you're pausing this somewhere along there. Please make sure you were listening and trying to figure it out. If you just blindly copy it down without thinking, well, then you're just copying stuff down. So I hope this is kind of fun for you. This time I'm going to say AV bisects CM, and we're trying to figure out what is our conclusion. What do we want to prove? More accurately, we could say, what can we actually prove? And I get a lot of people saying, see, this is a decoy, just to try to get you from sorting fact from what you want to believe. I mean, I get a lot of people saying these two isosceles triangle, two right triangles, perpendicular, all this stuff that we don't even know about. But here's the thing. AV is what? It's a segment. C and CM is a segment. All the rest of this, you don't know anything about it. This diagram is the same as this one, or this one, or this one. All you know is that this segment bisects this segment. Put in your tick marks and the truth comes out. What could you write? Well, I guess you could have said either way. You could have said CV congruent to VM. That'd be a nice conclusion. Or I suppose you could say V is the midpoint of CM. I'm going with the first one, and then I'll just say, if a segment bisects a segment, then it divides a segment into two congruent segments. And that is it. So that one, definition. Well, congratulations. You have made it through your second set of proofs on the Introduction to Proof chapter. So, well, write these out, send them in, and see you all in class.